5. Grading 9.5 binomial theorem. For those of you guys just joining us, pause the video right now. They were in the back of their homework spiral. I'm sorry, pause now. They were back in the homework spiral trying that one. We'll come back to it in 1 second. But number 10. Final answer, 792. Not a lot that you could have reduced, but 5 and 2 makes 10. 3 and 4 makes 12. 11, 9, and 8. Oh, that's not too bad to multiply. Whoa, number 18. They had you do Pascal's down to the 10th power row, third term. Should have been 45. Number 24. What did you guys do in number 24 to the 5th power? Did you guys actually do NCR like 5 times, 6 times, I should say? Or did you do 1, 5, 10, 10, 5, 1? Yeah, I think I would have done that too. Not that the NCRs are bad on this one, but if it's small, I don't know. I think Pascal's is a lot easier. You would have just done it up above. But then you had to simplify because you were using A is y and B is -2. So here's your final polynomial expansion. Number 32 is a bit nastier. Let me zoom in a little bit because that's kind of, well, it's not disgusting. I've seen much worse problems. You guys did RREF this semester, right? But it does take a little bit of work. So you still, once again, have 1, 5, 10, 10, 5, 1. But man, the numbers got all messed up when your A was 2x and your B was -5y. Final expansion you can see. And number 50, you were jumping, which you could have jumped by writing out the whole expansion like this and then counting 1, 2, 3, 4, 5. Or you could have realized that the 5th term, do you guys notice that they gave you a lot, or at least I gave you a lot, evens with the 5th power? Yeah. So shouldn't you by this time have gotten down the 1, 5, 10, 10, 5, 1? And then shouldn't you also have realized, like in this problem, that the 1, 2, 3, 4, 5th term is going to have x to the 1 and y to the 4th? Or A, well, I guess we would have called this x because there are a's. X to the 1 and y to the 4th. Nice. Then all you needed was your 1, 5, 10, 10, 5, 1. And plug and chug. Does anybody have a trick or a clue that they're using to get to the 5th term without, like, killing their brains? You don't know? Do you think about how the power is 5 and so there are 6 terms? Is that helping anyone? Yeah, that's true. I didn't mean so much, like you don't necessarily have to memorize this, because you could do Pascal's pretty fast on the test. I don't think you'd have to memorize the 1, 5, 10, 10, 5, 1. But yeah, you could have kind of gotten the pattern down for that. But I was thinking more like which one you're looking for. Not just the coefficients, the 1, 5, 10, 10, 5, 1, but also like which terms, because that's the problem. Don't you have to figure out what power to raise him to and what power to raise the second one to? So there are a few different ways of remembering. One is it's a 5th power. There are 6 terms, so then your 5th term is second to the last, which means this guy hasn't fully gone to the 5th power. He's at the 4th power. You could also actually count and think, okay, if I've gone through 5, 5, 4, 3, 2, 1, my first term is at the 1. Or you could think R is going to end up being the nth term minus 1 every time. There are different tricks, but ultimately you just need a way that works for you to find the correct term. Number 54 was a trick problem. I mean, it wasn't. It's very mathematical, but some of you did something illegal. They said, find the term that has x to the 8th. But did you guys notice what got plugged in to the A spot? So, question, what's the highest power of x if x squared is getting raised to the 12th? X to the 24th is your first term. And then x to the 22nd, and then x to the 20th, and then x to the y. They're all going to be evens. There are no odds. There is no like x to the 1 to multiply to make it odd. Evens, but it starts at the 24th and counts down to the 8th. So is the 8th like really close to the 12th? Really close to the highest? No, the 8th is actually on the other side. It's not one of the first terms, it's one of the last terms, because how many terms are there in this sequence, guys? Or in this expansion? No. 12 is the power. How many terms? 13, because we have all the powers of x, and then we have a constant at the end. Doesn't a quadratic, a binomial squared, get a trinomial? Ax squared plus bx plus c. So a second power has 3 terms. A 12th power has 13 terms. So disappear in the 13th term? Okay. So then in the 12th term, wouldn't the power be x squared? In the 10th term, wouldn't the power be x to the 4th? In the 9th term, wouldn't the power be x to the 6th? In the 8th term, wouldn't it be x to the 8th? There are a few different ways of thinking about this, and that's just what I was explaining, was how to move through like all 13 terms and figure out that x to the 8th is way over here, almost gone, as far as x to the 24th getting down to the 8th. But there was another way. Didn't Kathleen yesterday, when she was doing the warm-up problem, and we were asking her to show us her work, wasn't she using that, that formula for the nth term, right? So what if we were to bring that formula back? That's the general formula, like general, right? If that's the general formula, general, how do we make it specific to this problem? What can we plug in? I heard someone say A. What is A? Okay, so squared for A. What else can I plug in? Yeah, what is n? 12. So then it'd be 12 minus r. And then who's my b? Okay, who am I missing? R. Now hold on. What do I need this to equal? So couldn't I do 2 times power to a power you multiply? 12 minus r is equal to 8. Can't I make a baby equation and be like, hey, I need you to be 8, please? Now some of you like not tricky, but discovery people, experimental people, you like just playing around with the numbers. You could have probably been like, hey, 2 times 4 is 8, so then that has to be 4. So 12 minus what is 4? R must be 8. But if you did it that way, you literally just did the math, but in a very creative way. Couldn't we also do the exact same math, like actually solving the equation? And if we, not divided by 4, sorry. If we divide by 2, we'll get 4. 12 minus r has to equal 4. Add the r, subtract the 4, r equals 8. Either way, you end up with r equals 8. So if r equals 8, I can say, sweet, 12, c, 8, a to the 12 minus 8, 3 to the 8. Does it make sense how they got their term? So why was this one hard? It wasn't starting at x to the 12th counting down to x to the 8th. It was starting at x to the 24th counting down every other power to x to the 8th. And so it might have been easier to go to the general term and then say, hey, here's my x guy. X guy, I need you to be this dude. And then basically, technically, I didn't show you this, but it's really just the one-to-one property, because you have x squared to the 12 minus r equals x to the 8th. Guys, what do we do when we have like bases? One-to-one property, just look at the powers, right? And so I could have rewritten this as x to the 2 times 12 minus r equals x. Sorry. But ultimately, like you saw me do, it's the one-to-one property. We're setting 2 times 12 minus r equal to 8 and solving. And then basically it's a plug and chug at that point, right, guys? Cool. I thought that was probably one of the trickiest ones of homework as far as figuring out which term they actually wanted. The coefficient was 3 million, no, sorry. Yeah, this is a typo. That shouldn't be a point. That should be a comma. Sorry, 3,247,695. And last but not least, in number 88, you were plugging in 1/2 for A and 1/2 for B and plugging and chugging and solving and getting 0.273. Whoa, 0.273. Doesn't that look like a percentage? Maybe you're like, nah, it's not a percentage. Okay, fine. But what if it was a percent? 27.3%. I wonder what kind of scenario would be having us plug into the binomial theorem to get 27.3%. Was this a word problem, or was it just like a plug and chug? In number 88, oh, I don't have it open. I forgot. Did anybody else find it was weird that probability showed up in section 9.5? Because in number 88, ooh, did you guys see there are patterns in Pascal's triangle? Anyway, there are tons of patterns in Pascal's triangle. Weihart likes that a lot. She's the one that we watched the infinite Saharan caravan going off in the distance the other day. But anyway, coming back. To find the probability that the sales representative in exercise 87, there's a sales representative in exercise 87. What's he doing? He's making a sale. Okay, well, that's exciting. All right, well, anyway, there's a sales representative making a sale. Cool, go team. But what they're saying up here is to find the probability the sales representative in 87 makes 4 sales when the probability of a sale with any customer is 1/2, evaluate the term. So somehow the probability is 1/2 and gets plugged into the A spot. He's making 4 sales, so there's 4 successes, but I think he's making 8 sales total, which means 4 successes and 4 failures. So A has a meaning, B has a meaning, 4 successes, 4 failures, and we have a total of 8 different attempts that he's making with 4 successes. Interesting. Probability and this NCR thing somehow have to do with each other. And with that, cool kids, we're going to section 9.6, probability, as soon as we answer any questions that you guys might have that we didn't go over. So any odds, any evens? Tony, what's up? 61. Anything else? Yeah. 59. We don't like the ones right around there. All right, let's go look at 59, 61, and then we'll be done. 59, oh, page before, lo siento. 59 and 61. Oh, 2 different sections, though. 59 says find the, ooh, do you see why this is another trick question? How is this guy harder than most of the other examples? He's squared. Any of the ones with squareds are nasty. Not impossible, just nasty. So Gavin, I'm going to do the exact same thing we just did, but in a little different context. Well, actually, hold on. Someone who understood what I just did. You hear me talk all day long, and my voice is tired. So, who wants to tell me what to do? Aiden's avoiding eye contact. Tony, what do I do? Oh, okay, so he's thinking of the highest degree. Like that? No. Oh, you need it to equal x to the 8th, okay. So am I doing this one? Okay. What can I plug in, Tony? Good. Good. And it's 10. Okay, now what? Good. Because I need it to be 8. And that's what it currently is. So in math, we can make an equation anywhere we need it, right, guys? So Tony said 8 needs to be power to a power multiply. So then after some work, Tony, what'd you get R to equal? I think 6. How many of you guys actually solve by like dividing by 2, getting 4, subtracting 10, negative 6, dividing by a negative 1? How many of your heads started doing the algebra? Okay, and how many of your heads were like, wait a minute, 2 and 4 makes 8, so let's make this 4. This will be 4 if R is 6. And then the rest of you just stare at it blankly. Okay, so my 4 people that think about equations. Isn't this algebra 1? Solve for r? Okay. You realize why I'm a little... Okay. Whew! R equals 6. Oh, wait a minute, but hold on. That wasn't the answer to Gavin's question. I mean, that's the process. But how do we actually answer? What were they asking, bud? Were they asking for the coefficient? Perfect. So then, Gavin, you tell me, how do I finish this off now that I know r is 6? Yeah. Do you hear him? Say it louder. But this is not going to be a part of the coefficient. This just gets me x to the 8th. This isn't going to contribute to the coefficient. It's just y to the 6th. Since they had no numbers, that's the only coefficient, yeah. But if there was like a 2, we'd have to consider that, or a 3, we'd have to consider that. But in this one, since it was just variable, he's the coefficient. So solve him, you're good. Good job, bud. So now we're going to number 61, the next section, which says, oh, did you guys have a square root? Aren't I fun? Aren't I fun? We're supposed to expand using the binomial theorem. Hey, who has it memorized by now? What's Pascal's triangle for the third power?
1, 3, 1.
I think, right? Because it's 1, 1, 1, 1, 2, 1, 1, 3, 3, 1.
4, 6.
Yeah, 1, 4, 6, 4, 1. Okay. So. Oh, wait. This is the third power. I don't know why I was starting at the fifth. Where do we start for the third power? 3. And then 2. And then, uh-oh. But don't I need one of those guys? And then, does that make sense? First guy, which is going to be our A, is going to be cubed squared first and then gone. Second guy, which is going to be our B, is going to be gone, then first, then second, then third. Remember, they count opposite each other. And what's chilling in front? Our 1, 3, 3, 1. So all I got to do is plug and chug. Now, is the book going to have that in the back? No. Because it's going to make it all nice and pretty, right? So it's going to have something like, oh, 5 and 3 makes 15. And a square root squared is just an x. Or a 25 and 3 is 75 with a square root of x. And then 5 cubed is, come on, mental mathers, I should make you think. Good, 125. 5 quarters, $1.25. And then this one, well, you could do it a couple different ways. You could do the square root cubed, or you could write it the square root of the cubed, or you could write it x to the 3 halves. What did they prefer in the back when you guys went to check? Did they prefer the radical form or the fractional exponent form? Oh, fractional exponent. I guess that makes sense, though, because he doesn't have anything. So I suppose to write it all nice and pretty, you would have x to the 3 halves plus 15, x plus 75, x to the 1 half. I'm not sure it's beautiful, but it's right, so we'll say it's okay. Go team. Section 9.6, what were we talking about just a moment ago? Well, we weren't talking about it. You guys were. I wasn't involved in the conversation. So I'm bringing myself into the conversation. You place 8 pieces of paper numbered 1 to 8 in a box. You draw 1 piece of paper at random from the box, record its number, and then do what? Put it right on back in the box. And then I would say you probably shake the box, because then it says you draw a second piece of paper at random, so you don't like put it in and then like go reach for the other side. Little cheaters. So you mix it all up, and then you draw a second piece at random from the box and record its number. And I'm assuming, even though it didn't say it, you replace that paper as well. Oh, well, it doesn't matter, because that's all you're doing. You're just picking 2 pieces of paper. Finally, you add the 2 numbers. How many different ways does it say what's the probability? No. So were you finding the chances of doing this? No. You were just figuring out how many different ways it can possibly happen. Why is that helpful? As we get ready for section 9.6 and 9.7, as you guys saw a moment ago in section 9.5, NCR somehow has to do with probability, which means that whole binomial theorem, section 9.5, somehow has to do with probability. That whole binomial theorem was a sequence or series, which is why it's in chapter 9. Anyway, they all tie together in some weird, awkward way. But probability is section 9.7, and probability is the chances of something occurring. The chances of something occurring. Question, how easily can people get talked into gambling? Quite easily. Your ego a little bit. Just a little bit. Be like, oh, well, aren't you confident so-and-so is going to win? Why don't you bet on it? Right? Right? Okay. People make a killing on things like that. It's easy to get people talked into gambling on something. What could, besides like horrible debt and ruin, losing their house and their car and their job, whatever, besides those sorts of things, some bets are maybe not dangerous to make. Some of them are quite a bit more dangerous, especially depending on how much money is on the line and what kind of pattern it's forming. However, are some bets fairly low risk versus high risk? Maybe in retirement funds, or maybe even just for work, or maybe just for recreation. There are low-risk investments. Guess which one usually makes the more money? High risk. But what's the problem with high risk? It also loses the most money. Which is why is investing the same as gambling? Some people would say yes, some people would say no. But anyway, all this to say, do you think it's important to consider the risk? Not even going into the lifestyle and the danger and all that sort of stuff, but just the risk involved. Do you think it's important to consider? Yeah. Okay. So it's trying to figure out the chances or the odds of something happening. It could be something as simple as it raining today, and do I have to take an extra jacket or wear shoes that aren't going to get soaked? When you're considering the chances of something happening or the odds of something happening, what kind of mathematical expression will it always involve? Yeah. But the chances of it raining, or the chances of you on a certain bet, or chances of, if you think of the chances of, the odds of, the probability of, kind of mathematical. And percent comes from division, aka fractions. Right? Right? Okay. So if, for instance, at the very beginning, all you were betting was who was going to finally win, like the final winner, without considering people's stats or their scores or anything else, just thinking about the pure math of it all. If you made practice, what would be the chances of you picking the winner correctly? 1 in how many teams there are, right? Oh, there we go. Anyway, so we'll say 1 in 68. True? Are those great odds? All these other factors, right? But Kyle just said 1 in 68. What was the beginning of even considering the risk involved with your bet or the odds of your bet winning? How many possible winners there are? How many possible teams? What do you see up here? How many different ways? Before we can get to section 9.7 and start talking about odds and chances and fractions, and say, okay, how many successes over how many total? Oh, how many ways you can win versus how many ways total of it working out? We have to actually talk about how to calculate how many ways. Okay? So before we get to probability, before we get to odds, before we get to fractions, before we get to percentages, before we get to any of that, we just have to think of how do we count up things? How do we figure out how many possible? So in this case, we're not figuring out the odds or the chances, even though we could. We're just trying to figure out how many ways could this work, because before we can even think about whether it's wise or foolish or a good bet or not, and we're not going to go into all of that. But even before we start at the very beginning of, okay, what are the pure mathematical chances of, we have to figure out how to add up the possible outcomes. So how many different ways can you obtain a sum of 12? Well, guys, did you figure out all the different possible pairings? You could have picked a 1 and then a, nope, 1 and nothing makes 12, at least not with papers 1 through 8, right? So if you pick a 1, what'd you just do? Lose. True? Okay, how about a 2? Nope, because there's no 10. I just lost. How about a 3? Nope. How about a 4? Yes. So 4 and 8. You could have picked a 4 and 8. What else could you have picked? A 5 and 7. What else could you have picked? A 6 and 6. What else could you have picked? A 7 and 5? What else could you have picked? An 8 and 4. What is the question you have to ponder? So you could have picked a 4 and then an 8, a 5 and then a 7 and then a 5, an 8 and then a 4. Could we have chosen that 6 and then that 6, and that would be an extra one? Why not? There's only one piece of paper labeled 6. So you picked up the 1, 6, and then you picked up the 1, 6 again. There is no like red and blue, and they're different 6s, and they can add, right? So what are the different pairings? 1, 2, 3, 4? Yeah, just 5. Why was that easy? Well, because you could think of them all in your head and say, okay, 1 and, nope, 2 and, nope, 3 and, nope, 4 and, 4 and 8, 5 and, 7. 6 and, 6. 7 and, 5. 8, 4. 9 and, not 3. Because 9's not a piece of paper. Counting's not too bad if you can actually visualize, well, either see, be given, or visualize all the possible options and pick out the ones that are good. When does counting get hard? He's alive.
When you get decimals and fractions.
Well, we're not getting decimals and fractions, though. Remember, we're just counting up how many ways something can happen, like your 1 and your 64. We're not putting them together to get fractions or decimals. So it's not going to get hard with fractions and decimals. That's section 9.7. It's going to get hard when we can't contain in our head all the different possible outcomes. Because then all of a sudden, how do we start counting them all up if we can't even visualize them? Yeah?
How do you find the probability of winning?
My expertise is not that high.
Of 64 and 64 to 64.
You mean your entire bracket being perfect? You should know to some degree if it's just like who won which matches or which games towards the final championship and then who wins the final. You'll know that by the end of section 9.6 and 7. Just the pure math of it, not going into the actual like, hey, which team is better and this guy's going to be like coming from behind. And you'll know by the end of 9.6 how to figure out how many different possible brackets there are. And then there's only one winner. Does that make sense? So 1 out of. But only with the winners of the matches, not with all the extra point spreads and all that jazz. Okay. Considering all outcomes and counting up, I'm going to say the successes, but right up above, there's another way of saying successes, the favorable outcome. Because, for instance, a favorable outcome might be it not raining today. So be careful. Success, the success is it not raining. That's weird. Success is a negative, like a anti-statement. Yeah, sometimes. So be careful. Success isn't always whatever event happening. Sometimes it's the event not happening. But either way. The old-fashioned way is just count it up. Have all of them in front of you and just count. 1, 2, 3, 4. So for the bracket situation that Kyle was asking, the old-fashioned way would literally be to write out every single possible variation of the bracket and then count them all. Horrendous. Well, for someone who does the tic-tac-toe, maybe it's not. But coming back. Sometimes there are too many to count. Okay, yes, we all agree. Sometimes there are too many to count. So we need some sort of principles to guide us. We need some sort of formulas probably, and then some other clues, like is repetition allowed or not? Like in our example, was the paper being put back or was it being kept out? That changes things, possibly. Because if the paper was being kept out, wouldn't you have never gotten the 6 and 6? Principles, formulas, other clues. Don't worry, we're not in with them. We're going to go talk about what they are and what they include. So, counting principles. Well, before we get to counting principles, what do you guys think would be a smart way of attacking this problem? Do we have to go thinking about counting principles and formulas and clues, or is this an old-fashioned count it up? Determine the number of ways a computer can randomly generate one or more such integers from 1 through 12. Count it up, because isn't 1 through 12, we can actually picture in our heads 1 through 12, right? All at once, but still, numbers 1 through 12, we got it. 1, 2, 3, 4. Okay. Divisible by 4. How many ways can a computer randomly generate one or more? Hold on, it just says 1. One integer divisible by 4. How many ways? 3. 4 and 8 and 12. We can hold in our mind the numbers and be like, hey, by 4, 4, 8, 12, and then we're done. Cool. We got 3 ways. How about 13? How many ways can the computer generate 2 distinct? Why are they saying distinct? Why is that clearly necessary? No repetition. But, okay, would you repeat 4.5 and 4.5 to get 9 anyway? No, because it says integers, counting numbers, 1 through 12. Oh, okay. Well, I wouldn't have done 4.5 and 4.5 anyway, but if this was 10, 5 and 5 would not be allowed. Huh.
Could you do 12 and negative 3?
Good thinking, though. Good thinking, though. Adam.
When it says distinct, like 1 and 8, those are distinct because they add up to 9, which still count as like 8.
Ooh, what's Adam asking? He said 1 and 8, they're distinct because they're 2 different ones, but would 8 and 1 be a distinct, like a separate variation? What do you guys think? Does the computer choose them all at once, or do you think the computer chooses them in an order? In order, yeah. A computer is going to accomplish one task at a time. Even though it might all come out at the same time, technically it's doing tasks in order. So is 1 and 8 different than 8 and 1? Yeah. Okay, what else can make 9? 2, 7, and 7 and 2? And then? Both of these did them the old-fashioned way. Why? Well, numbers 1 through 12 aren't so hard for my brain to figure out. But what if I was to say 1 through 1,000? Ready, set, go. I think we'd want to figure out some sort of clues, hints, tips, and tricks, especially for the divisible by 4 one. Adding up to be 9, well, there's only so many ways because 9's a small number. But how about adding up to 89? That's a whole lot more. Okay, let's keep going. So, even though some problems are able to be counted up the old-fashioned way, even just from the guys talking about their brackets or us talking about the numbers 1 through 1,000, oh, come on, there has to be better ways, and there are. Not so much better ways, but just ways that can be applied to problems with big sets of data. If one event E1 can occur in M1 different ways, oh, there are variables. That's okay. E for event, M, I don't know, just 'cause. If one event E1 can occur in M1 different ways, followed by a second event, E2, occurring in M2 different ways, the number of ways E1 and E2 can occur, we have to multiply. Multiply. Hey, M for multiply. Maybe M for multiple. Oh, interesting. Either way, I want you guys to consider the following event. Example, I should say. How many different pairs of letters from the English alphabet are possible? Stink. A, B, A, C, A, D, A, E, A. Ugh. But do you guys realize that if we were to count them all out, we'd have to do A with every single one of the 26 letters, and then B with every single one of the 26 letters, and then C with every single one of the 26 letters? Hold on. Aren't you going to have 26 letters with 26 letters? Oh, we're mathy, aren't we? 26 columns and 26 rows. You can kind of think of that. What's the dimension of that going to be? 26 columns, 26 rows, how many entries? 26 times 26, isn't it? Does that make sense, guys? If we were to list all of those out, it'd be 26 letters with 26 letters. It's going to be a 26 by 26, which means, Adam, you already found it, 676 different pairs without us having to write down a single one. Nice. I don't want to write down every single one, let alone count them all. Now, how many of those are actual words? Well, that's a whole different problem for a whole different day. And not even in this class, to be honest. But whenever you see something in homework, like how many 3-letter words, 4-letter words, 5-letter words are possible? Whenever you see that, guess what they mean? Do they mean actual, look it up in Webster's Dictionary words? No. How about Webster's Dictionary and Urban Dictionary? No, we're not even going there. All they mean is 3-letter groupings, 2-letter groupings, regardless of whether or not it makes an actual word. Does that make sense? So when you see words in homework, don't actually think, oh no, I have to see which ones are legal. No, that's not. Guys, what's the main thing for today? And for specifically this first fundamental counting principle? We can figure out how many, when thinking of different characteristics needing to be true at the same time, like your bracket system, how many with multiplication with and separating the two events. So what if we had something like a license plate? Now, depending on where we are, the license plates might have different restrictions as far as, we're not even going into like customizable plates, just like the basic ones. We're not even talking about California. We're talking about a certain state. No idea which state they're talking about. Maybe it's a pretend state. Each automobile license plate number consists of 2 letters. This is a really awkward license plate. Followed by 1 and 2 and 3 and 4 numbers. So I have a letter, I have a letter, I have a number, number. I'm just showing blanks as in like placeholders. Yeah? To get a license plate, aren't I going to have to put something there and there and there and there and there and there? Why did I just put multiplication? What word was I using over again? What word was I using in separation of one letter and another letter and another letter and another letter? Oh, sorry. And a number and a number and a number and a number. And, thank you. The one word I've been saying over and over and over again. And. Sweet. 26 letters, at least in the English alphabet. 9 numbers, no 10 numbers. 1 through 9 and the number 0. Oh, so 26, 26, 10, 10, 10, 10. Ha! Oh, but wait. To avoid confusion between the O and the 0 and between the I and the 1, the letters O and I are not used. So how many letters are legal? 24. Anything about the numbers, though? Careful. To avoid confusion between the O and the 0, the I and the 1, only the letters. Nice. Oh, so don't I just put in 24 options, 10 options, 10 options, 10 options? How could you get a computer to list off all the different possible license plate numbers? Because aren't they going to have to do that somewhere in order to be able to generate and give someone a license plate number and take it off the list and not use it again? How is the computer going to do that? How about list out the 24 letters? And then each of the 24 letters with each of the 24 letters. And then each of the 24 letters with the 24 letters, each with the 10 different numbers. And then with the, you could just make this huge branching effect of all these different options. But how many different possible options are there? What's 24 times 24, anybody? 576, and I need 1 and 2 and 3 and 4 zeros. 1, 2, 3, 4. Guys, what are the numbers going to be in homework? Big. We're not going to get to decimals and percentages and fractions until section 9.7. Section 9.6, the numbers are going to be big. Now, normally we would try to get through this last example, this last page, before we are done with today. However, today is a unique day because today is March 13th. Which means tomorrow is March 14th. There's going to be a big old table, actually probably 2, just 1 or else my smart board's going to die. 1 big old table. And you guys can get 3.14 extra points in your test quiz category if you bring a circular treat that can be shared, that is store-bought or restaurant-bought, cannot be homemade. Does it have to be dessert? No.
Pizza.
Ooh, or bagel bites. Oh, that's homemade. I don't know how you would do that, not homemade. But anyway, something circular. Why? To celebrate pie. Or I guess it could be something with the pie like etched in, but I don't know how you're going to do that from a store or from a restaurant either. What's something circular? Donuts. What else is something circular? Cookies. What else is something circular? Coffee cups. Maybe I'll have coffee made for you tomorrow. Now hold on, wait. If you bring something circular that can be shared, hold on, pause. Will a package of little baby Oreos from the Snack Shack count? No. That can't be very shared, right? Done. So, something circular that can be shared does not have to be a huge party pack of anything. You don't have to go out and spend tons of money. However, something circular that can be shared amongst the class, at least half the class can have some. Now, hold on, wait. Am I supposed to carry around this circular treat that can be shared all during period 1? That's awkward. No, my room will be open. It will be available. Now, on the table itself, only the period 1 spread to start the day, right? Whatever they have